In finding the UMP test, we have already discussed the use of Neyman-Pearson lemma. Now, in the present lecture, we are going to introduce a very important property for a class of distributions which is known as the monotone likelihood ratio property. First, we shall define the MLR property or the monotone likelihood ratio property. Then we discuss some examples starting with the one parameter exponential family. Some specific situations will be discussed. Next, we shall discuss some examples where the distribution do not belong to the one parameter exponential family. Finally, we shall prove a very important theorem by which one can determine the UMP test for testing H naught theta equals to theta naught against theta greater than theta naught when the distribution Px theta has the MLR property with respect to some statistic Tx. In the present module, we define the monotone likelihood ratio MLR property for a family of PMF or PDF denoted by set of all Px theta, theta belongs to script theta subset of real line. We exploit this property to derive the UMP test of size alpha for one-sided null against one-sided alternative hypothesis in some situations. First, we shall discuss the MLR property of a family of distributions. A real parametric family Px theta, theta belongs to script theta subset of real line is said to have MLR property in a real valued statistic Tx if for any theta 1 less than theta 2 belongs to script theta, the following are satisfied. Number 1, Px theta 1 is not equal to Px theta 2, that is distribution are distinct corresponding to distinct parameter points. Number 2, the ratio Rx which is equals to Px theta 2 by Px theta 1 is non-decreasing in Tx on the set of all x such that maximum of Px theta 2 comma Px theta 1 greater than 0. Note that if Px theta 2 equals to 0 and Px theta 1 greater than 0, Rx equals to 0, and if Px theta 2 greater than 0 and Px theta 1 equals to 0, Rx equals to infinity. First, we shall discuss some examples on MLR families. First, we consider the one parameter exponential family that we have discussed in an earlier module. If Px theta belongs to the one parameter exponential family, then we can express Px theta in the form Px theta equals to u theta into exponential q theta into Tx into Vx, such that u theta and q theta depends only on theta, whereas Vx is independent of theta and Tx depends only on x. We set Tx such that q theta is a strictly increasing function of theta. Then we have for theta 1 less than theta 2, Px theta 2 divided by Px theta 1 is equals to u theta 2 by u theta 1 into exponential Tx into q theta 2 minus q theta 1, which is increasing in Tx because q theta is a strictly increasing function of theta. Hence, the family Px theta where theta belongs to script theta has MLR in Tx. It is to be noted that if x1, x2 up to xn is a random sample of size n from the population with PMF or PDF Px theta, then Px theta has MLR in summation I from 1 to n Txi. Let us consider the following examples. Let x1, x2 up to xn be a random sample of size n from normal theta, 1 population. Therefore, Px theta is equals to 1 by 2 pi to the power n by 2 into exponential minus half into summation over I from 1 to n xi minus theta whole square, which is equals to exponential minus n theta square by 2 into exponential theta into summation over I from 1 to n xi into 2 pi to the power minus n by 2 into exponential minus half into summation over I from 1 to n xi square. If we set u theta equals to exponential minus n by 2 theta square, q theta equals to theta, tx equals to summation over I from 1 to n xi, and vx equals to 2 pi to the power minus n by 2 into exponential minus half summation over I from 1 to n xi square, then Px theta has MLR in summation over I from 1 to n xi. We consider the next example. Let x1, x2, xn be a random sample of size n from normal 0, theta square population. Therefore, Px theta is equals to 2 pi to the power minus n by 2 into theta to the power minus n into exponential minus half summation over I from 1 to n xi square. Now, if we set u theta equals to theta to the power minus n, q theta equals to minus 1 by 2 theta square, tx equals to summation over I from 1 to n xi, and hx equals to 2 pi to the power minus n by 2, then we see that Px theta has MLR in summation over I from 1 to n xi square. Next, we consider our third example. Let x1, x2, xn be a random sample of size n from Bernoulli theta population. Therefore, Px theta equals to theta to the power summation xi into 1 minus theta to the power n minus summation xi, which is equals to 1 minus theta whole to the power n into exponential summation xi into log theta by 1 minus theta. If we set u theta equals to 1 minus theta whole to the power n, q theta equals to log theta by 1 minus theta, tx equal to summation xi, and vx equals to 1, then we see that Px theta has MLR in Tx equals to summation xi. We consider our fourth example. Let x1, x2, xn be a random sample from the geometric distribution with PMF Px theta equals to theta into 1 minus theta whole to the power x. Here the joint PMF of x1, x2, xn is given by Px theta equals to theta to the power n into 1 minus theta whole to the power summation xi, which is equals to theta to the power n into exponential log 1 minus theta into summation xi. If we set u theta equals to theta to the power n, q theta equals to log 1 minus theta, tx equals to summation xi, and vx equals to 1, then Px theta has MLR in Tx, which is equals to summation xi. We consider another example. Let x1, x2, xn be a random sample from the population with PDF theta into e to the power minus theta x, where x greater than 0. Here px theta equals to theta to the power n into e to the power minus theta summation xi, which is equals to theta to the power n into e to the power theta into summation xi minus summation xi into Vx, where we set Vx equals to 1. Now, if we set u theta equals to theta to the power n, q theta equals to theta and Tx equals to minus summation xi, then Px theta has MLR in minus summation xi. We consider another example. Let x1, x2, xn be a random sample from the population with PDF 1 by theta into e to the power minus x by theta. Here Px theta equals to 1 by theta to the power n into e to the power minus 1 by theta into summation xi. If we set u theta equals to 1 by theta to the power n, q theta equals to minus 1 by theta, Tx equals to summation xi and Vx equals to 1, then we see that Px theta has MLR in summation xi. Next we consider some distributions which do not belonging to the exponential family. First we consider the distribution Cauchy theta, 1 population. Here Px theta equals to 1 by pi into 1 plus x minus theta whole square. For any theta 2 greater than theta 1, the ratio Px theta 2 by Px theta 1 is equals to 1 plus x minus theta 1 whole square divided by 1 plus x minus theta 2 whole square. This is greater than 1 as x tends to theta 2, it is less than 1 as x tends to theta 1, and this ratio tends to 1 as x tends to plus minus infinity. Thus, Cauchy theta, 1 distribution is not a member of MLR family. Next we consider another example where x follows Cauchy with parameter 0, theta. Here Px theta equals to theta by pi into theta square plus x square. For any theta 1 less than theta 2, the ratio Px theta 2 by Px theta 1 is equals to theta 2 square into theta 1 square plus x square divided by theta 1 square into theta 2 square plus x square, which can be written as theta 2 square by theta 1 square into 1 minus theta 2 square minus theta 1 square divided by theta 2 square plus x square, which is increasing in x square or in mod x. Thus, Cauchy 0 theta is a member of MLR family with MLR in mod x. We consider another example. Let xi follows rectangular 0 theta for I equals to 1 to n independently. Here Px theta equals to 1 by theta to the power n if 0 less than x ordered n less than theta equals to 0 otherwise, where x ordered n is the largest order statistic. Now we take theta 1 less than theta 2, then the ratio Px theta 2 by Px theta 1 is equals to theta 2 by theta 1 whole to the power n if 0 less than x ordered n less than theta 1, and this is equals to infinity if theta 1 less than x ordered n less than theta 2. This is non-decreasing in x ordered n. Thus, rectangular 0 theta is a member of MLR family with MLR in x ordered n. We consider another example where x follows hypergeometric distribution with parameters theta, small n and capital N. Here theta is unknown. Here Px theta is equals to theta Cx into capital N minus theta C small n minus x divided by capital N C small n. where maximum of small n minus n plus theta comma 0 is less than equals to x less than equals to minimum of theta comma n. Here px theta plus 1 by px theta is equals to theta plus 1 into capital N minus small n minus theta plus x whole divided by theta minus x plus 1 into capital N minus theta, which is equals to 0 if x equals to theta plus small n minus capital N, and this is equals to infinity if x equals to theta plus 1. This ratio is non-decreasing in x. We can use the above to provide the following general version. Let us take any theta 1 less than theta 2, then px theta 2 by px theta 1 is equals to px theta 1 plus 1 divided by px theta 1 into px theta 1 plus 2 divided by px theta 1 plus 1 into into px theta 2 divided by px theta 2 minus 1. This product is increasing in x. Hence, the family of hypergeometric distribution has MLR in Tx equals to x. Now, we consider the following result, which is due to Carlin and Rubin in 1956. This is known as Carlin-Rubin theorem. For testing h theta equals to theta naught versus h a theta greater than theta naught corresponding to MLR family px theta, theta belongs to script theta in Tx. The test given by phi x equals to 1 if Tx greater than c equals to some constant a if Tx equals to c is equals to 0 if Tx less than c, where c and a are such that expectation of phi x under theta naught, which is equals to probability under theta naught Tx greater than c plus a into probability under theta naught Tx equals to c, this is equals to alpha, which belongs to 0 1, where alpha is the size of the test. Then phi x is UMP of size alpha for testing h against HA. We consider a proof of the theorem. Take any theta 1 greater than theta naught. Then by NP lemma, MP size alpha test for testing h theta equals to theta naught against theta equals to theta 1 is given by phi x equals to 1 if px theta 1 greater than k into px theta naught equals to some constant a if px theta 1 equals to k into px theta naught equals to 0 if px theta 1 is less than k into px theta naught, where k greater than equals to 0 and a belonging to the interval 0, 1 are such that expectation under theta naught phi x equals to alpha. Let us write Rx equals to px theta 1 divided by px theta naught, which is a function of Tx. We write this as g of Tx, where gTx is a non-decreasing function of Tx. This is because the family px theta has a MLR in Tx. Now, let us set C equals to infimum of Tx such that gTx greater than equals to k. Then the above test function can be written as phi x equals to 1 if Tx greater than c equals to a, if Tx equals to c equals to 0 if Tx less than c, and it satisfies the condition expectation under theta naught phi x equals to alpha. such a test being independent of any theta 1 greater than theta naught, and hence it is UMP of size alpha for testing H theta equals to theta naught versus H A theta greater than theta naught. In the present lecture, we have seen that the MLR property plays a very vital role in determination of the UMP test. We have seen that some of the common distributions, say normal distribution, binomial distribution, or geometric or exponential distributions has the MLR property, whereas the Cauchy distribution with parameter theta and 1 does not have this property. We have also seen that the hypergeometric distribution and the rectangular 0 theta distribution and also the Cauchy 0 theta distribution have the MLR property.